Oh no, it's Freddy Full House. I'm not playing this guy. He always gets a full house. It's ridiculous. It's like a 99% chance of getting a full house whenever we tell the hand.
It's crazy.
That's right. And by now it's impossible to lose money because of my enormous streak of full houses.
Actually, if the cards are shuffled properly and no one's cheating, each hand is independent of the others, and your hands have absolutely no statistical effect on the next hand.
What? I'm not a cheater. I'm Full House Freddy. Of course I always get a full house. Who invited this guy?
My facts are right, and your hands are also independent from your nickname. And there might be a good reason to think you'd be cheating. How many hands did it take until Freddy won last time?
2.
Well, according to the respected statisticians of 888poker.com, the probability of drawing a full house is 0.1441%. P is 0.001441. So, if we calculate the expected trial that you should win on, it would be 1 over P, 1 over 0.001441, which comes out to be 693.96, or about the 694th trial, which is far from the second trial. The probability of you getting a full house on your second hand would be 1 minus P to the n minus 1 times P, which comes out to be 0.001439.
Nuh-uh. Actually, the statistical significance of my result proves otherwise. Assuming that the expected number of trials to success, or the mean amount of trials to success in infinite runs, is 693.96, we can take a z-score of x bar minus mu, or the standard deviation, which if we look at the AP formula packet, is standard deviation of x equals root 1 minus p over p for geometric distributions. So 2 minus 693.96 divided by root 1 minus 0.001441 divided by 0.001441 is only 0.9978 standard deviations below the expected number of trials to success, with a p-value of 0.1587, which is pretty high relative to the numbers you've been putting up. My result isn't even statistically significant under a significance level or alpha of 0.05 or 0.1 or even 0.15.
Nice try to trick me and your comrades, but we are discussing a geometric distribution. It looks like this. What you need to get a z-score and a p-value is this normal distribution. So let me talk about the difference between those distributions. The normal distribution, also known as the Gaussian distribution or bell curve, is a continuous probability distribution. It's symmetric and bell-shaped with a single peak at a mean value. The distribution is defined by 2 parameters, the mean and the standard deviation. The area under the curve is equal to 1, representing total probability. It's continuous, meaning it can take on any real value within the certain range. The probability density function of a normal distribution is defined by the famous bell-shaped curve. The probability mass function of a geometric distribution describes the probabilities of achieving success after a certain number of trials. The geometric distribution is discrete, imagine lines here. The distribution takes on non-negative integer values representing the number of trials until success. It models the number of independent and identical trials needed to achieve the first success. The distribution is skewed to the right, with a long tail on the right side. So, the normal distribution, continuous, symmetric, bell-shaped. Geometric distribution, discrete, skewed to the right, represents the number of trials until success. The normal distribution models continuous data. The geometric distribution is suitable for analyzing discrete events with a fixed probability of success, like this. So, you wrongfully used a normal distribution where you shouldn't have, and the statistic you came out with is false.
Whatever, forget about it.
But hey, still, maybe you just got really lucky on that second hand. Let's check another probability. How many hands did you guys play last time?
Oh, 30.
And how many times did Freddy get a full house?
25 times.
Using that same success parameter of P is 0.001441 with n equals 30 trials, the number of successes that are expected in 30 trials should be n times P, or 30 times 0.001441, which comes out to be 0.0432 successes, or full houses in this case, which rounds down to 0, far from his result of 25. The probability of getting 25 or more full houses in And 30 hands would be 30 combination 25 times P to the 25th, and then 1 minus P to the remaining 5 failures, not successes, and then you repeat that for 26, 27, 28, 29, all the way to 30. I don't have time to do that, so I would just do that on a calculator with binomial CPI. After you do that, you will get a probability that is so low that it just reads 0.
But if you take the z-score for...
Again, you have to assume a normal distribution before getting a z-score or p-value. See, the binomial distribution isn't like a normal distribution, which we described earlier. The binomial distribution takes on non-negative integer values from 0 to n. It is commonly used to analyze binary outcomes, such as the number of successes or failures, yes-no events. The probability mass function of the binomial distribution describes the probabilities of obtaining each possible number of successes in a given number of trials, just like this 25 out of 30 that we're talking about here.
Wait, why are you saying all this?
I'm saying that according to geometric and binomial probability calculations, Freddy's poker hand patterns have been statistically near impossible.
Whatever, you ruined my day. Now I'm triggered. I'm heading out.
I don't want to play with this guy if he's cheating.
Yeah, but his father owns this place, so Freddy can't get kicked out. Let's see. We come to this casino on weekends, so we have to find out how many hands Freddy plays in a weekend when we all come here. If we find out he plays a majority of the hands on average each weekend, then let's just play poker somewhere else.
Good idea. I'm tired of losing money to this guy. Well, I know that he plays on Friday, Saturdays, and Sundays. He plays a mean of 30 hands and 20 hands and 40 hands respectively those days, with respective standard deviations of 10, 5, and 15.
So how many hands does he play in a weekend?
Shoot, I wish I was good at math.
Well, when we combine means, we add them together. The mean for Friday, Saturday, Sunday, 30 plus 20 plus 40 is 100 hands of poker played per weekend. To find the standard deviation, we would take the square root of the sum of the variances of hands played Friday, Saturday, Sunday by Freddy, and that would come out to be the square root of 10 squared plus 5 squared plus 15 squared, which will get us a standard deviation of approximately 18.7083. To get a reference, how many hands is played here each weekend?
About 150, with a standard deviation of 2.
Well, that means on average, on a given weekend, when you guys play poker here, Freddy plays a majority of the hands. So you guys might want to consider playing poker somewhere else.
Thanks for clearing that up. Let's cancel our memberships. I'm tired of losing all my money to this guy.
Me too, man.